We continue now to the field of quantum instrumentation. Our next speaker is Andrea Orzati. He's CEO of Zurich Instruments, which he joined in 2024, but brings extensive experience in growing and scaling technology businesses. He worked in previous roles as an ASIC designer at U-Blocks, board member at Techable, and executive positions at Sensirion. He's a bit special this morning as he's a speaker. Well, he holds a PhD, but it's not in physics. It is in microwave electronics from ETH Zurich. Andrea, please welcome Andrea for the next talk. Thank you.
So, thank you very much. Grégoire gave away my deepest secret. I'm an engineer in front of a bunch of physicists, so we'll try to do my best. And also, I am aware I'm the last person standing between you and the coffee break. So I will try to be more relevant than I can. So Zurich Instruments is a company that started many years ago, and 10 years ago, we started to engage with the quantum computing world. And what I'm presenting today, it's kind of a wrap-up of the last 10 years that we have been working in this world. So mainly focused on quantum computing and quantum computing control electronics. And together with this wrap-up and this perspective, also, I'm going to share some of the challenges that we think are going to be solved from a quantum control electronic perspective if we have to materialize the roadmap that Sarah, the speaker from IBM, was showing in the previous slide. So we talked about algorithmics and the problems that quantum algorithms can solve and the applications. But what I want to say here, quantum computing is more than the qubits technology, so the quantum part and the high-level algorithmics. It is also about the control electronics. And this is a fundamental part of a quantum computer and a fundamental enabler for what quantum computing is, from the research into the scaling of big quantum computing. So Sarah said it much better than I can. So we start with the application software on top, so all these algorithmic that are trying to solve problems in quantum computing. Then you compile them down, and then at this stage, the control electronics start making its work. So basically taking this and compiling this information into pulse level, so generating a sequence of electronics control signals that are going down to the qubits and making the qubits do what they should do and reading the information out of them. And that is done usually with classical instrumentation, so electronics that comes into boxes, and there's a lot of boards and FPGA and RF microwave or optical parts. And then at the bottom of the stack, you have the very important quantum devices, so that the core technology, the qubits that enable the functionality. So this is what we do, and maybe some words about Zurich Instruments. We were founded in 2008, a startup from the Physics Institute of the ETH in Zurich. We are around 200 people in Zurich. We are growing, and we are a global company. In 2021, the company was acquired by Rohde & Schwarz. It's a big instrumentation company. It's a Bavarian group with over 90 years of history. And I think it is important to be part of the Rohde & Schwarz group. I want to say that because it is a private company, very long-term oriented, with deep pocket and access to a lot of technology. And as you will see from these challenges that I'm going to talk about, this is something you need when you are trying to build control electronics for quantum computing. So this is one of the roadmaps you find from big quantum computer players. And what you see is that this is a roadmap to, let's say, quantum advantage, to building a useful quantum computer. What you see there, you start from the qubits technology, then you start quantum error correction with the goal of having the so-called logical qubits, which is then long-lived, is stable and stays there. And then you scale this up into more complex systems until you have the big systems that are generating quantum advantage. And what does it mean, if you look at this roadmap from the perspective of a company that is doing quantum control systems? Let's start with the end, the scaling part. So I think there, what we clearly see, there will be a path in the other where the functionalities will be somehow frozen. Everything will be converging to a dominant design, and then scaling, we push those technology for control electronics that can achieve the right performance, but also the right price point. If you're controlling 10 qubits or if you're controlling 1 million qubits, there is a lot of electronic difference in there, and you cannot spend the same amount of money as you do when you control 5 qubits, when you control 1 million. But when this is going to happen, what you are going to have, you will still have research in other fields of quantum computer. So the qubits optimization, we will not end. So it will keep going on. So we will have this research trust, both in companies and in academia, that is still going on. And you will also have the search and the refinement on algorithmic, such as quantum error correction, in order to make the logical qubits more scalable, using less resources and more performant. So what does it mean? So it means if you are in quantum control instrumentation, you need to have, let's say, different product lines that are covering different needs of all the industry that is in front of you. And you will have some of your customers that are just playing in one of these fields, maybe at academia or in smaller reality. But if you are engaging the scaling customers, you will be playing in all these fields at the same time. And then, of course, software and bringing everything here together with a software that is controlling your electronic, that is giving the best infrastructure and linking all the data and everything together, it's going to be fundamental also here. So if you look at the future and you move so which problems is a control electronic must be able to solve, or which challenges are we facing for the future? So let's start. One thing is qubit fidelity. So you have your qubits, and this is a topic where control electronics has a role, as an influence. Then we are talking about quantum error correction. And then another challenge is reducing the cost per qubit. So we're going to talk about this. And the final one is having a software environment that links all of them for the customers into a seamless experience, into a productive environment for our customers. So qubit fidelity, so the qubit fidelity is, of course, very much controlled by the technology of the qubits, but the analog performance of the control electronic has a direct influence on gate and readout fidelity. So that's very important. And the requirements are that you have minimal imperfection in the signal and maximal stability over time. And so what it should not happen is that your control electronic becomes a bottleneck for fidelity and for reaching fidelity. So that's what is the forbidden thing here. Second challenge, we have heard about mitigation and error correction in quantum computing. So you need basically in a control electronic to be able to measure from the quantum systems, and from this measurement apply algorithmics with the lowest latency time so that you can resend the results of this algorithmic back to the system before something has happened and the error propagates further. So you can also measure syndromes, or you can measure emit circuits, apply and feed forward. But what is important here, and the key message of this is that you will have algorithmics that you have to run, classical algorithmics that you need to do, and they have to be able to run either on your control electronics, maybe on a dedicated GPU, or on dedicated ASICs on external HPC resources. And here, the control electronic must be an enabler dealing with the lowest possible latency for the system. And then we go to the next challenge, which is scaling the cost per qubit down. And so if you look now, so cost per qubits, let's say it's for single qubits in an academic experiment bigger than, let's say, 10,000 Swiss francs, dollar, euros per qubit. So it's a quite expensive things to do, And these, and I'm talking about the control electronic part here, this has to go down with time. And at the end, if you have productive quantum computer, you will be needing to offer lower than, let's say, 100 Swiss francs or dollars or euros per qubit that you control cost to your customers. That's very, very important. And here there are different enablers that can help. You can pack signal and multiplex them in some smart ways and send them down to the quantum systems. You can use some electronics that you move, for example, for superconducting qubits into the cryostat, or develop specific ASICs that are working there. So there are a lot of things that you can do. I also think that with time, a part of this cost driving will be also given to standardization and also to the capabilities of having mass manufacturing at scales, available in the company, so that you can really produce at low cost and high quality. So it's going to be a mix of a lot of different factors here. Software. Software in a quantum computing world plays, in control electronics plays many different roles. The first role is, this is a system, it's a product, so software should be making your system easy to use, intuitive, and automate as much as possible the different tasks that should be performed by the control electronics. So automation and ease of use are two big parts. So there are a lot of tedious, lengthy procedures that you do when you bring qubit experiments to life, and this should be taken care by the control electronics in an automatic way, so that you don't have, to sit down and wait for your system to do stuff. You can press a button and, let's say, let everything run, for example, overnight. So this is about efficiency and using the brain power of the researchers in the best possible way. If you look at scaling, when you take algorithmic and then you compile them down to pulses that you need to send to all the qubits, I think what is key is time. So you have to be able to perform these compiling steps in a very fast way, so that the algorithmic, so that this is not a bottleneck in the experiments, and you can have real life feedback from what it's doing. And so this is an example here where moving from one language to the other, you can really reduce this time. So that's the end of my talk. And these are the key takeaways that I would like to give to everybody here. So a controller electronic plays a pivotal role into building a quantum computer. And the main challenges are the fidelity, the quantum error correction, solving the cost per qubit challenge, and making sure that you have a software and automation environment that is enabling the customer to be more effective and more productive. Thanks a lot, and I'm ready to take questions.
Thank you very much. Thank you, Andrea.